This lecture is over 2.4, Permutations and Combinations, and really we're going to use the same idea in what we talked about in 2.3, but we're going to use some formulas to find the number of combinations and permutations. So, our objectives today are going to be develop and apply the permutation formula and the combination formula. So these will be given to us later, but really the important part in this section is knowing when to apply the permutation formula and when to apply the combination formula. So that's going to be important. And then we're going to also talk about the number of ways to determine distinguishable permutations. So we'll talk about, a lot of times this is used with words. So if I say, Saul, and I say I can rewrite this as SWA, I could write it as AWS, and so forth. So we're going to be able to distinguish how many different permutations are possible, and we'll get to examples like that. So, from last time we talked about the fundamental principle of counting, and we used tree diagrams to show how this ends up working out. But the fundamental principle of counting allows us to determine the total number of possible outcomes when a series of decisions must be made. If more than one item is selected, then we can either talk about it with replacement or without replacement. So we did some examples of that in 2.3. Without replacement or with replacement. That has to do with like being repeated or not repeating. So if I'm pulling 3 letters out from the alphabet to make a word, if I can replace those letters, then I would have repeats, like AAA would be a potential word. Without replacement means once I pull it, then I can't put it back in. So let's look at some meaning here. This is important with and without replacement. So selecting items with replacement means the same item can be selected more than once. After a specific item has been chosen, it is put back in the pool for future choices. Selecting items without replacement means the same item cannot be selected more than once. After the specific item has been chosen, it is not replaced. So we can look at an example of a 4-digit personal identification number, like your PIN number for your bank account or your debit card. In this case, digits are selected with replacement. It's very likable you could have 1111 as a PIN number. So your PIN could be 36666. The same digits can be selected more than once. So when counting the items selected with replacement, we use the fundamental principle of counting. For our first number, we have 10 choices. Our second number, we have 10 choices. The third number, we have 10 choices. The fourth number, we have 10 choices. So we have 10,000 different possible 4-digit PINs. In many situations, items cannot be selected more than once. So for instance, when selecting a committee of 3 people from a group of 20, you cannot select the same person more than once. So for my 30 students, if I say, okay, I'm going to group you into groups of 3, I can't put the same person in more than one group, and I can't have one group made of 3 people that are the same, if that makes sense. So the tricky thing in this section is to know when we're doing an example with replacement or without replacement. And you're going to have to look to the contents of the question to know, okay, we're picking with replacement or without replacement. So when selecting items without replacement, depending on what order the selection is important, we're going to talk about a permutation and a combination. So always with permutation and combination, it's without replacement. So keep that in mind. If we're doing anything with replacement, you're going to use the fundamental counting principle. So very important distinction here. If I do something like 2.3, if I say something about the license plate and the numbers can be replaced, like AAAA could be a license plate number or whatnot, then you would not use permutations or combinations. Permutations and combinations only work with things that are being not replaced, so without replacement. So let's look at a permutation. Permutations are when more than one item is selected without replacement from a single category. And the order of the selection is important. So the order is important. That's the important thing on a permutation. So permutation, the order is important. So you could think of permutations P, so important, I don't know, there's a P in there. So the order is important. So if it matters which order you pick them, it's called a permutation. And this is the formula for permutation. So you might have actually used this formula in 2.3, but you didn't know it was actually the permutation formula. So if I give you n objects selected R at a time, so R items selected without replacement from a pool of n items. So I might say something like, I'm going to, out of my 30 students, I'm going to pick the 5 people to present on Monday, if this was an in-class group and we actually met in a classroom. How many different ways I have to pick 5 from 30, and order matters because 5 from 30, so I have 30 people to pick from and I'm picking 5, and the order would matter because that means if I pick you first, that means you're going to have to present first. If I pick you second, you present second. So 1, 2, 3, 4, 5 is a different permutation than 5, 4, 3, 2, 1. So if I picked you to present first or if I picked you to present last, this is a permutation. So the order matters here. So you're going to have 30 factorial over 30 minus 5 factorial. You can think of this as the fundamental counting principle too, because what you end up getting is you have 30 choices for your first one. 30 times 29 times 28 times 27 times 26. 27 times 26. You end up getting the same answer as you would with the fundamental counting principle simply because this is what the math is going on here. Really, I have 30 factorial over 25 factorial. So if I expand this out, 30 times 29 all the way down to 25 factorial over 25 factorial, the 25 factorials cancel and I'm left with 30 times 29 times 28 times 27 times 26, which would be the fundamental counting principle. I have 30 choices for this one. Once I pick someone here, I have 30 choices. I have 29 choices for this spot. Once I pick a person here and a person here, I have 28 choices left. So keep that in mind. A lot of times there's more than one way to look at this, more than one correct way to look at it. So for a permutation in which the order selection is important, we're going to use a permutation. If I'm just picking 5 people and it doesn't matter what order I pick them, that's called a combination, and we'll learn about that later on. So the example on your PowerPoint has to do with 6 local bands have volunteered to perform at a concert benefit, but there is enough time for only 4 bands to play. There are also some concerns over the order in which the band will perform. How many different lineups are possible? Well, you could think of, okay, I only have 4 spots. That's a small band, right? 4 spots here. And I have 6, then 5, then 4, then 3 possible choices, right? I have 6 bands to choose from here, and then I have 5 bands here, and so forth. Or you can think of it as 6 permutation 4, which would be 6 factorial divided by 6 minus 4 quantity factorial. So then this is 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1. The 2 times 1 cancel, and you're left with 6 times 5 times 4 times 3, which is exactly what would you get with the fundamental counting principle. So combinations are going to be when the selection, the order of the selection may or may not be important. So you always take it without replacement. So whatever we're doing here, we're doing without replacement. And the order of the selection is not important. That's called a combination. And the formula for combination looks like a permutation, except you have one extra term. And the R term here is dividing out any of the repeats. So if I say something like 1, 2, 3, if I'm picking 3 students to be in a group, and it doesn't matter the order I pick them, if I pick 1, 2, 3, or 2, 1, 3, that's the same group. So here you divide out by the repeats, and that's always R factorial. So you're still taking R items without replacement from a pool of N items, but the order does not matter. So order is not important here. So let's look at this example. A DVD club sends you a brochure that offers any 5 DVDs from a group of 50 of today's hottest releases. How many different selections can you make? Well, order doesn't matter. It doesn't matter if I pick the first DVD or the 5th DVD. I still get 5 DVDs. I don't get one faster than the other, or it doesn't matter here. The lineup doesn't matter. So I have 50 choices, and it's a combination, and I'm picking 5 from 50. So looking at my formula, I have 50 factorial over 50 minus 5 factorial times 5 factorial. So I would have 50 factorial over 45 factorial times 5 factorial. And you might have evaluated a problem like this in 2.3. But I could put this in my calculator, straightforward like we did in 2.3, right? I could have 50 factorial divided by open parentheses 45 factorial times 5 factorial in parentheses, and I get, what do I get? 2,118,760. 2,118,760. And you can check yourself with your calculator, and this is also on your PowerPoint, so you can go to your PowerPoint. It's in your book as well, so you can follow along with your book. Another way you can enter it is the 50 factorial would be 50 times 49 times 48 times 47 times 46 times 45 factorial. The reason I decided to stop at 45 factorial is because I have a 45 factorial in my denominator. So the 45 factorials cancel, and I could do 50 times 49 times 48 times 47 times 46 divided by my 5 factorial, because that's how many different ways I could rearrange picking 5 DVDs. I could pick the first one, then the second, third, fourth, fifth, or I could pick the 5th one, then the first, second, third, and fourth. It doesn't really matter what order I write them down on. So that's why you can still kind of see the fundamental counting principle here, except then you're always going to divide through by the repeats for combination. To me, you got to be careful, because I think combination, the order matters, because I think like a combination lock, but that's not true. So do not think of it that way. Combination, the order does not matter. Permutation, the order is important. So you use a permutation when the order is important. These are on your PowerPoint in your book. So if I give you this formula, if R is 0, if I want to do 5, choose 0, well, that's going to be 5 factorial over 5 minus 0 factorial. Combination, I use this 0 factorial. So by definition, 0 factorial is 1. If you plug in your calculator and you plug in 0 factorial, that's always 1. Oops, sorry. 0 factorial is 1. You can see it here. Factorial 0 is 1. So here I end up with, let's see, skipping over here. I have 5 factorial on top over 5 factorial on bottom. 5 factorial times 1, right? 5 factorial over 5 factorial is 1. So your answer here is 1. If I do 5 choose 1, 5 choose 1, I have 5 factorial over 5 minus 1 factorial times 1 factorial, which would be 5 factorial over 4 factorial, which would simply be 5, right? So expand this out a little bit more. So this would be 5 times 4 factorial over 4 factorial. The 4 factorials cancel, and your answer here would end up being 5. Just to finish, this out, 5, choose 2. So I have a 5 factorial on top, a 5 minus 2 factorial on bottom, divided times a 2 factorial. So I have a 5 factorial over 3 factorial times 2 factorial, which would be 5 times 4 times 3 factorial over 3 factorial times 2 factorial. The 3 factorials cancel, and I'm left with 20 over 2, which would be 10. 5, choose 3 would be a 5 factorial over 5 minus 3 factorial times 3 factorial, which ends up being the same thing as I have up here, right? Which would be 2 factorial times 3 factorial, which is the exact same thing as I have here. So my answers end up being 10 again. 5, choose 4. So I have 5 objects, and I'm choosing 4 of them. How many different ways can I do that? I have 5 factorial over 5 minus 4 factorial times 4 factorial. So that's 5 factorial over 1 factorial times 4 factorial, which is 5. And then the last one, 5, choose 5. I end up with 5 factorial over 5 minus 5 factorial times 5 factorial, which ends up being 1. So how many ways can I pick 0 objects from 5? There's only one way to pick 0 objects, that's picking none. How many ways can I pick 1 object from 5? There's 5 different ways to do that. I could pick the first one, I could pick the second one, I could pick the third one, the fourth one, or the fifth one. I only have 5 ways to do that. How many different ways do I have to pick 2 objects from 5? It turns out there's 10. 3 objects from 5, there's 10 ways. 4 objects from 5, there's only 5 ways. And then 5 objects from 5, there's only 1 way of picking 5 objects from 5. So if you see here, this is the 6th row of Pascal's triangle. This would be picking 5 objects, picking 0 of them from 5, 1 from 5, 2 from 5, 3 from 5, 4 from 5, or 5 from 5. And you can see that by examining the diagram in this figure, each row or each number in the triangle is the number of the sum of the 2 numbers in the row immediately above it. So you notice that this 3 comes from adding 1 plus 2. This 2 comes from adding 1, 1. This 3 comes adding 2, 1. This 6 comes from adding 3 and 3. This 10 comes from adding 4 and 6. So if I wanted to do the next row, I would always have a 1, 6, 15, 20, 15, 6, and 1. So if I want to look at 6 objects, there's 1 way to pick 0, there's 6 ways to pick 6, there's 15 ways to pick 3 objects, there's 40 ways to pick 4 of the objects, there's 15 ways to pick 5 of them, there's 6 ways to pick 6 of them, and there's 1 way to pick 6 of them. Sorry, I got off 1. 0, 1, 2, 3, 4, 5, 6. So there's 1 way to pick 0 of them, 6 ways to pick 6 of them, 6 ways to pick 1 of them, 15 ways to pick 2 of them, 20 ways to pick 3 of them, 15 ways to pick 4 of them, 6 ways to pick 5 of them, and 1 way to pick 6 of them. So this is known as Pascal's triangle. It's a really useful tool when we talk about, and once we get to algebra, if you ever get to algebra, Pascal's triangle can be used for expanding out things. At this case, you're really not going to apply this. It's just kind of a fun little use of Pascal's triangle there. You're just going to be asked to randomly calculate one of these. You won't have to do a whole bunch of them. So really in this section, it's really important to know which technique you're going to use. And like I said before, there's more than one technique that might work if you're looking at it correctly. So you kind of want to ask yourself, can the items be repeated? If so, then if yes, you're going to use the fundamental counting principle, what we learned in 2.3. If no, are there more than one category? If there's more than one category, you're going to use the fundamental principle of counting for each category, and then figure out if you want to use a combination or permutation. If the order matters, you use a permutation. If the order doesn't matter, you use a combination. So it's possible you use a combination of all three counting principles in one problem. And you can go through this box that is on your PowerPoint, and you can ask yourself, you know, how many is being selected, and it gives you the permutation and combination there. So the last thing we're going to talk about is a permutation of identical items. So the only formula your book gives is here. And basically you take how many total items you have and divide out by any repeat. So X, Y, and Z would be your repeats. So let's look at an example here with Mississippi. Mississippi has 11 letters. So on top I have 11 factorial. But the I is repeated 4 times. So I don't know why they use X, Y, and Z here. So I is repeated 4 times. So I need a 4 factorial on the bottom. Because if I switch the letters I and I still have Mississippi. If I switch it with this I still have Mississippi. And this I still have Mississippi. So you cannot tell when I switch the I's. So that's why you divide out by the number of I's you have, factorial. S is repeated 4 times, so that's why you have a 4 factorial here. And P is repeated twice, so that's why you have a 2 factorial in denominator. This is your repeats. You divide out by any repeats. So you divide out by any repeated items. So if I plug this in my calculator, I get 34,650. That's how many different ways I could rearrange the letters in Mississippi to have unique representation. Notice that 11 factorial is 39 million. Oh, I left a number out there. We should fix that. Let's see what 11 factorial is. 139,16800. I left the 1 out. So there should be a 1 here. Right? Yeah. So 39,916,800 different permutations. But since we have some repeats, since I is repeated and S is repeated and P is repeated, it's dividing out by any combinations that are the same. You only actually get 34,650 different ways versus the 39 million different ways or different permutations. So let's look at examples from the homework. A group of 11 seniors, 9 juniors, 5 sophomores, and 4 freshmen must be selected from a committee of 4. 1 person from each class. This is the fundamental counting principle, right? You're picking 1 person from each class. You have 11 choices for your seniors, 9 choices from your juniors, 5 from your sophomores, and 4 from your freshmen. So you just multiply that to any mixture of classes. Well, the order doesn't matter, right? So we're going to talk about a combination versus a permutation. So that's the thing to decide here. I have 11 plus 9 plus 5 plus 4. So total I have 29 students. I have 29 students and I want to know how many different ways can I pick 4 of them, right? So 29 students and I'm picking 4 of them. The order does not matter because if I pick one of them first and one of them second, they're still going to be on the same committee. It's not like one's a president and one's a vice president. So I would have 29 factorial over 29 minus 4 factorial times 4 factorial, right? Because a combination, the order does not matter. Where did my combination go? And I'm going to divide out by the repeats, and that's where my extra 4 factorial comes from. So you should be able at this point to calculate this. exactly 2 seniors. So that means I have 11 people, or 10, I have 11 people to choose from, and then I have 10 from my senior group. Then from my other 2 groups, I have 9 plus 5 plus 4, so, oh, that 19, 9 plus 5 plus 4, 9 plus 5 plus 4, 18, sorry. So 9 plus 5 plus 4 gives me 18. Then I have 18 people left, and if I use one of them, I have 17. Another way to do it is then I have 18 choose 2, because I'm picking 2 people, or you can use the fundamental counting principle here. For the first one, I have to pick a senior, and there's 11 seniors. For the second one, I have to also pick a senior, and since I picked a senior here, there's only 10 left. So you could think, oh, well, then there's 18 other students to pick from, and if I pick one of them, I have 17 left. Or you can think of that as 18 times 17 is going to be 18 choose 2. And you can do the math to see that's going to be the same. In an art class consisting of 11 students, all of them must present their portfolios and explain their work to the instructor and their classmates at the end of the semester. If the names are drawn from a hat to determine who goes first, second, and so on, how many presentation orders are possible? So order matters, right? Because who goes first, who goes second. So this is a permutation. I have 11 students, and I want to find the permutation of so it's going to be 11 permutation of 11. So it'll be 11 factorial over 11 minus 11 factorial, which is 11 factorial over 0 factorial, which is simply 11 factorial. Which should make sense is because if I had 11 blocks, I would have 11 times 10 times 9 times 8, right, and so forth, times 1. So I have 11 times 10 times 9 times 8 times 7, which is 11 factorial, which might be faster to plug in your calculator as 11 factorial than 11 times 10 times 9 times 8, so forth. If their names are not, or if their names are put in alphabetical order and determine who goes first, second, and so forth, how many presentation orders are possible? 1. Sometimes students get caught up on this because they're trying to force it into a formula, but if they're in alphabetical order, then you already have your presentation order, and there's only one possible presentation order. That's set by alphabetical order. So this is the last one I'm going to do from this section, and it's interesting because the last one, the order is important. So I want to pick 4 people from 16. No distinction on the possible members. So this is just going to be 16 combination 4. I'm just picking 16 people. I'm picking 4 people from 16. It doesn't matter what order I pick them. So 16 factorial over 16 minus 4 factorial times 4 factorial. That will give you your answer. If one person is the chair and the rest are general members, that means I have 16 people to pick from the chair, but then I have 15 people remaining, and I'm picking 3. So I take 16 times this number. If one person's the chair, one person's the secretary, one person's responsible for freshmen, and one person's responsible for cleaning up, then this is really a permutation. I take 16 permutation 4, which is going to be 16 factorial over 16 minus 4 factorial. So you can think of this as 16 times 15 times 14 times 13, right? I have 16 choices here, 15 here, 14 here, 13 here. I have times 12 factorial over 16 minus 4 is 12 factorial, so the 12s cancel. So you can see this is the same as fundamental principle of counting, with this idea of just throwing it into a permutation and getting your answer versus thinking about how many chairs we have available. So hope this helps. If you have any questions, let me know. Don't get too frustrated in this section. There's a lot of watch it, so you can watch them do that. Be careful because all the red things will change. So if you're doing a watch it and it says 15, and then the next time you try it, it will say 14, you're not going to be able to put that same answer in. So good luck, and let me know if you have any questions.